Hi, this is Prathami, and I welcome you all to another new episode of the 24th Universe. And today I have for you Boolean Algebra. In this video, we will see what is Boolean Algebra, what is a truth table, what are Boolean operations, what is the order of precedence of Boolean operators, what are Boolean laws, an example to solve the Boolean expression using the laws of Boolean algebra, and lastly, the applications of Boolean algebra. Boolean algebra is the branch of algebra. It differs from elementary algebra in two ways. First, the values of the variables are truth values, that is, true and false, usually denoted as 1 and 0, whereas in elementary algebra, the values of the variables are numbers. Secondly, Boolean algebra uses logical operators such as conjunction, that is, and disjunction, or, and the negation, not. Elementary algebra, on the other hand, uses arithmetic operators such as addition, multiplication, subtraction, division. Boolean algebra is therefore a formal way of describing logical operations in the same way that elementary algebra describes numerical operations. Therefore, we can define Boolean algebra as a branch of algebra where the values of the variables are the truth values true and false, usually denoted as 1 and 0, and uses logical operators such as AND, OR, and NOT operators to perform logical operations. Boolean algebra was introduced by George Boole in his first book, The Mathematical Analysis of Logic, that is in 1847, and set forth more fully in his In an Investigation of the Laws of Thought in 1854. In the 1930s, Claude Shannon introduced switching algebra as a way to analyze and design circuits by algebraic means in terms of logic gates where one could apply the rules of Boole's algebra in switching circuits. Boolean algebra was invented after the binary numbers were discovered. To know the history of Boolean algebra, you can watch my earlier video, that is the history of binary code, and the link is given in the description. In Boolean algebra, only two values are used, true and false, known as Boolean variables or truth values. True value is also known as digital on state and false value is also known as digital off state. These values are represented with the bits 1 and 0. They do not behave like the integers 1 and 0 for which the 1 plus 1 equals 2, but here in Boolean algebra 1 plus 1 equals to 1. Because, as I just mentioned, in Boolean algebra, 1 means true and 0 means false, and plus means or. So, if either of the values are true, the result is true. That is, true or true equals to true. Now let us look at the truth table. A truth table is a structured representation that presents all possible combinations of the truth values for the input variables of a Boolean function and their corresponding output values. Now, how is this drawn? First, the column is made for each of the variable terms. Under these columns, all the possible combinations of A and B is listed out for A and B. A and B can both be either 0 or 1 and can form pairs such as 0 0, 0 1, 1 0 and 1 1. Each of these pairs should make up one row in the table. To know how many combinations a certain number of variables can make, 2 raised to n is used where n is the number of variables. Then, a column is made for the actual expression itself. In this column, the resultant value for each row is written. So, here in this example, the values for A and B are both 0. So, a 0 is written in the first row. Then continue the same thing for the rest of the rows. And that's the truth table. Remember, for long expressions, it will be wise to break it down and make multiple columns. Now let us see Boolean algebra operations. Boolean algebra operations can be classified into two groups, basic and secondary operations. Basic operations. Boolean algebra has three basic operations: conjunction, disjunction, and negation, expressed with the corresponding binary operators and, or, and the unary operator not, collectively referred to as the Boolean operators. Secondary operations. Operations composed from the basic operations such as the exclusive or XOR, material biconditional or logical equivalent or XNOR, and material conditional or implication are called as the secondary operations. Now let us discuss all these operations in detail. But before that, let me tell you in brief about the logic gate. A logic gate is a device that performs logical operations on one or more binary inputs that produces a single binary output. Various logic operations, that is and, or, not, can be performed physically by using the different combinations of the logic gates. The primary way of building logic gates is using diodes or transistors acting as electronic switches. The logical operation can be expressed as an algebraic expression known as the Boolean expression. So, if we have Boolean expression, we can perform the respective logic operation using the logic gates, and vice versa. That is, if we have logic gates, then we can write the Boolean expression. I would like to tell you, a universal gate is a gate which can implement any Boolean function without the need to use any other gate type. The NAND and NOR gates are called as the universal gates. It is nothing but a complemented and complemented OR. In practice, this is advantageous since NAND and NOR gates are economical and easier to fabricate and are the basic gates used in all IC digital logic families. Now, we shall discuss different Boolean operations. The first is the AND operation. For AND operation, the resulting value is true if the values of the two input variables are both true, denoted as, consider two input variables A and B. A dot B. This is how we denote A and B using a dot. Here is the truth table, and one can clearly see when A and B both are 1, the result is 1, otherwise it is always 0. And this is how we represent the AND logic gate. OR operation. The resulting value is false only if the values of the two input variables are both false, denoted as A plus B. This is how we denote A or B. In this truth table, one can find when A and B both are 0, the result is 0, otherwise it is 1. And this is how we represent the OR logic gate. NOT operation. This takes only one operand and hence known as the unary operator. The resulting value is opposite of the input variable, denoted as A bar. This is how we denote A naught, that is, with a bar on top of the variable. In this truth table, you can see when A is 0, A bar is 1, and when A is 1, A bar is 0. And this is how we represent the NOT logic gate. XOR operation. If the values of the two input variables are different, the result is true, and if the values of the two input variables are same, the result is false, denoted as A plus with a circle and B. This is how we denote A XOR B. In this truth table, when A and B are different, the result is 1, and when both A and B values are same, the result is 0. And this is how we represent the XOR logic gate. And these are the reduced forms of XOR expression. Next, we shall see XNOR operation. XNOR operation is also known as the mathematical biconditional or logical equivalence or Boolean equality operation. This is the exact opposite of XOR. So, here in XNOR, the result is true if the values of the two input variables are same and false otherwise, denoted as A circled dot B. This is how we denote A XNOR B. And In this truth table, one can see when A and B values are different, the result is 0, and when both A and B are same, the result is 1. This is how we represent the XNOR logic gate, and these are the reduced forms. The next operation is implication. Implication is also known as material conditional operation or conditional statements. A Boolean implication of the two input variables A and B is if A is true, then B must be true. It cannot happen that if A is true and B is false. This is how we denote A implies B with an arrow. Here in truth table, one can see that when A is 1 and B is 0, the result is 0, and rest all cases the result is 1. And this is how we represent the imply logic gate. And this is the reduced form used in Boolean expression. First of all, not everything can be written in the form of truth table. And yes, I know this implication truth table is the most confusing of all truth tables. Let me try to make it little easy for you with this example. Everyone knows that New Delhi is in India. So it is obvious that a person born in New Delhi must be surely be born in India. Now, consider two propositions denoted with A and B. A says the person is born in New Delhi. B says the person is born in India. Now, let us apply the implication truth table for A and B as follows. Row 00 says the person not born in New Delhi is not born in India. True, it is possible. That person is not born in any states of India and definitely not born in India. This might not be true at all the time, but it is not impossible. The second row, 01, says a person not born in New Delhi but born in India. True, this is also possible. Maybe the person is born in Goa, which is another state in India. So this is possible. Now the third row, 10, says a person is born in New Delhi but not born in India. No, this is impossible. A person, if born in New Delhi, must be born in India. It is obvious. So this statement can never be true. So it is a 0. The last row, 11, says a person born in New Delhi and born in India. This is very much true. It is 100% possible. So, except for 1-0 combination, which is false, rest of the combinations are always true. Even now, if you have not understood, then better memorize the truth table and you will understand with time. These are the summary of Boolean operations. A and B, A or B, A not, A XOR B, A XNOR B, A implies B. As you have already seen, there are many reduced forms for each of the secondary operations. You can use any of them which you can remember easily. Precedence rules. When used in expressions, the operators are applied according to the precedence rules. This is the table showing the order of precedence for the basic operations. Not is evaluated first and then and is evaluated and the last comes the or. For secondary operations, I suggest you use the reduced form in order to simplify the Boolean expressions. Now we shall see Boolean algebra laws. By simplifying the Boolean expression, we can simplify the number of logic gates used in digital circuit. Hence, we can simplify the digital circuit. Now, how to simplify the Boolean expression? For that, we should know the Boolean algebra laws, which we shall discuss now. The first is the commutative law. The commutative law states that the numbers on which we operate can be moved or swapped from their positions without making any difference to the answer. Consider two Boolean variables A and B. Or commutative law is A or B equals to B or A. And commutative law is A and B equals to B and A. And we can prove this expression using the truth table like this. Associative law. Associative law states that as long as the operators are the same, regrouping the terms in an expression does not change the value of the expression. Or associative law says A plus A or B or C equals to A or B or C. And associative law says A and B and C equals to A and B and C. A and B all together and then all to C gives a result which is same as the result of the variables B and C all together and then all to A. Similarly, A and B ended together and then ended to C gives a result which is same as the result of the variables B and C ended together and then ended to A. We can prove this expression using the truth table like this. Next is the distributive law. Distributive law for OR AND states that the multiplication of the two Boolean variables and adding the result with another Boolean variable will result in the same value as adding the Boolean variable with the individual Boolean variables and then multiplying them together. The distributive law for AND OR states that the addition of the two Boolean variables and multiplying the result with another Boolean variable will result in the same value as multiplying the Boolean variable with the individual Boolean variables and then adding them together. Or distributive law is A or B and C is equal to A or B and A or C. And distributive law is A and B or C is equal to A and B or A and C. And we can prove this expression using the truth table like this. Absorption law. Absorption law states that the complicated expression can be made into a simpler one by absorbing the similar variables. A or A and B is equal to A for OR absorption law, and for AND absorption law, A and A or B is equal to A. Here, A is a similar variable and the resultant answer is also A. This can be proved like this, and we can prove this expression using the truth table like this. Idempotent law. Idempotent law states that if a Boolean expression is operated with itself, the resulting expression will be equivalent to the original expression. For OR operation, A or A is equal to A. For AND operation, A and A is equal to A. Here, we see that A is ORed with A and the resultant answer is A itself. Similarly, A ANDed with A results to A itself. This can be proved like this. Here you have to remember something ORed with something is the same something. Something ANDed with something is the same something. Complement law. Complement law is also known as the inverse law. The complement law states that when something is ORed with its complement, the result is always 1, and when something is ANDed with its complement, the result is always 0. A or A bar is equal to 1, A and A bar is equal to 0. This can be proved like this. Here you can remember something ORed with its complement is 1 and something ANDed with its complement is 0. Identity law. Identity law states that each thing is identical with itself. A or 0 is A and 1 is A. This can be proved like this. Remember, something ORed with 0 is something itself. Something ANDed with 1 is also something itself. Annihilator law. Annihilator law is also known as the annulment law, dominance law, or null law. Annihilator means to destroy something entirely. Here the constants 1 in OR operation and 0 in AND operation destroys the variable in the respective Boolean expression. OR annihilator law, A OR 1 is equal to 1, and annihilator law, A and 0 is equal to 0. Annihilator law states that regardless of what the variable is, the variable when ORed with 1 will be equal to 1, and the variable when ended with 0 will be equal to 0. This can be proved like this. Remember, here something ORed with 1 is 1 and something ended with 0 is 0. De Morgan's law. The De Morgan's law states that applying complement operation to an entire AND or OR operation would change not only the operands but also the operator. A or B the whole bar is equal to A bar and B bar. AB the whole bar is equal to A bar plus B bar. Here in OR operation, we can see that the complement of OR of two variables A and B is equal to the end of the complement of each variable A and B. And in AND operation, the complement of AND of two variables A and B is equal to the OR of the complement of each variable A and B. Using the truth table, we can prove this expression like this. Double negation law. Double negation law is also known as the involution law. Double negation law states that taking the complement of the complemented term would result into the original term. That is, A bar the whole bar is equal to A, or A double bar is equal to A. Here, if A is equal to 0, A bar is equal to 1 and A bar is equal to 0. That is the original term itself. Remember, double negation of something is the something itself. The summary of laws, commutative, associative, distributive, and absorption law are like regular math and can be remembered easily. De Morgan's law and double negation law, these are to be remembered together, and the other laws can be remembered using this, can call it memory table. Green indicates the idempotent law, blue indicates the complement law, yellow indicates identity law, and pink indicates the annihilator law. One thing to note here, these colors have no connection with these laws. This is just to remember them easily. There are many ways to simplify Boolean expression in the digital system. They are as follows. Using the truth table, it can handle up to 3 variables comfortably. Beyond 3 variables, it becomes a little overhead. Using the Boolean laws, good for simplifying up to 6 variables. Using Karnaugh maps or K maps, good way to simplify variables and can be manageable up to 6 variables. Using the Quine-McCluskey method, it is automatized in a computer and works better up to 8 to 10 variables. Espresso heuristic logic minimizer, this method can handle many variables, maybe hundreds. For Karnaugh maps, you can watch my video whose link is in the description. Now let us see an example to simplify Boolean expression using the Boolean laws. Consider a Boolean expression A bar or B bar the whole bar XORed with A XOR B the whole bar. First step is to write the expression as it is. Then apply De Morgan's law to the left part of the main XOR like this. Then applying the double negation law, reduce the left part to A and B. Now solve another XOR, reduce it using the XOR reduction, and the bar will be as it is like this. And then apply De Morgan's law like this, where A here is AB bar and B is A bar B. And then again apply De Morgan's law to each of that term like this. Then further apply double negation law. Now cross multiply A bar with A plus B bar and B with A plus B bar like this. By the complement law, A bar A and B B bar reduce to 0 like this. Now the identity law says something ALLed with 0 is something itself. So A bar B bar ALLed with 0 is A bar B bar. Similarly, AB ALLed with 0 is AB itself. So we have this expression now. Now treat this expression as A XOR B, where A is equal to AB and B is equal to A bar B bar plus AB. That will give you this particular expression. Now apply De Morgan's law to the first part of the main OR and cross multiply the second part of the main OR to get this expression. Now just regroup the first product term like this. Now using the complement law, AB would be treated as A. So AB and AB the whole bar reduced to 0. Similarly, AB the whole bar and AB reduced to 0 like this. Now using the annihilator law, A bar and B bar the whole bar ended with 0 reduced to 0 like this. Now We know that something odd with 0 is something itself. So the expression reduced to ab the whole bar and a bar b bar. Now using the De Morgan's law to ab the whole bar to change the expression to this. Then apply the distribution law, that is multiply a bar b bar to a bar and then to b bar like this. Then use the idempotent law to reduce the expression to this one, that is a bar ended with a bar gives us a bar again. Similarly, b bar ended with b bar gives us b bar again. Later, use the OR idempotent law treating a bar b bar as a to further reduce the expression to this one. Then use the De Morgan's law again to get a plus b the whole bar as the simplified expression. By the way, the same thing can be solved using the truth table like this. We can see in the last column that it is similar to an OR operation but a complemented one. So, the simplified expression is a plus b the whole bar. Now let us see the applications of Boolean algebra. The most prominent application of Boolean algebra is to design circuits involving logic gates. Boolean algebra allows one to simplify Boolean expressions that make more compact Boolean expressions that require less logic gate, which simplifies the digital circuit. Boolean algebra is also called as algebras of logic because they are often used in two logical systems, that is propositional logic and set theory. Let us understand these things a little bit more. Propositional logic. The propositional logic is also called as propositional calculus, statement logic, sentential calculus, sentential logic, or zeroth order logic. It deals with propositions or a statement that can be true or false. Compound propositions can be formed by connecting propositions by logical connectives such as and, or, not, etc. It is related to Boolean algebra in a way that only minor changes in the notation and terminology have to be made. All Boolean variables become propositional variables. True is represented with capital letter T and false becomes upside down capital letter T. Example, consider the two propositions A and B. A says the sky is blue. B says the trees are green. A and B says the sky is blue and the trees are green. Set theory. In mathematics, a set is a collection of different objects. These objects are called as elements or members of set. Elements can be anything like numbers, symbols, or even other sets. A set may have finite or infinite number of elements. Each set is denoted by capital letters such as A, B, C, etc. A set may be represented using the roster notation or the set builder notation. Roster or enumeration notation defines a set by listing its elements between curly brackets separated by commas like this. Example, A is equal to 4213, B is equal to blue, white, red. Set builder notation. Set builder notation specifies a set as a selection from a larger set determined by a condition on the elements. Example, this is read as F is the set of all numbers n such that n is an integer in the range from 0 to 19 inclusive. Sets can be represented graphically using Euler and Venn diagrams. A Venn diagram uses overlapping circles to illustrate the logical relationships between two or more sets of items. Euler diagrams help bring clarity to complex relationships between multiple sets. The difference between Euler and Venn diagram is illustrated in the following example. Consider an example with two sets of numbers. Set A is equal to 1 to 5 and set B is equal to 3 and 4. Since these two sets do not have any common numbers, the Euler diagram on the left represents these sets with two circles that do not intersect. The Venn diagram represents the same set with two intersecting circles and the area of intersection is left empty. Consider another example. Set A is equal to 1 to 5 and set B is equal to 1, 2. The sets have numbers 1, 2 in common. The Euler diagram on the left visualizes the relationship between these sets with circles that include each other. while the Venn diagram on the right shows again intersecting circles with empty region B that is not A at the right. Consider another example which shows three sets of numbers. Set A is equal to 1, 2, 4, 5, 7. Set B is equal to 3, 4, 5, 8. And set C is equal to 2, 5, 6. Since each of the sets has common numbers with other sets, there are no empty intersections of circles or other regions of circles in this case. Therefore, the Euler diagram here is same as the Venn diagram. In this, the Euler and the Venn diagrams are both identical. Here, no sections are empty. Besides digital electronics and mathematics, some real-life applications of Boolean algebra include search engines, enhancing search algorithms by filtering results using Boolean logic and or not. Second, data mining, analyzing data sets to discover patterns and relationships. Third, database querying, constructing complex queries in SQL using Boolean operators. Fourth, control systems, designing control logic in industrial automation. Fifth, decision making systems, developing algorithms for artificial intelligence and machine learning. Sixth, network security, creating firewall rules and intrusion detection systems. 7. Programming, implementing control flow and decision making in software development, and so on. In order to start with practical experiments, one has to buy few things such as breadboard, few wires, few ICs, resistors, push button switches, and few LEDs. And that's it. I hope you have got some insights on Boolean algebra. If you have any doubts, please ask me in the comment section below. If possible, please do share my videos with others who might find this useful. Lastly, don't forget to like and subscribe to my channel for more such useful videos. Thanks for watching and see you again soon in my next video.